Georgia Tech has a number of strengths in high-performance computing. What's so unique is that we have the computing researchers who are designing new architectures, new systems software, new algorithms, and we also have some of the most capable application users of high-performance computing in aerospace engineering, in physics, in biology, and other departments. And that mix is what's necessary to solve the real-world challenges of our next generation. So high-performance computing at Georgia Tech combines not just computing, but our science and engineering applications. It's really applying future technologies towards solving real-world applications. For instance, we look at solving problems in transportation as we go forward with congestion in our cities. We look at deploying green information technology or green IT. We look at tracking severe storms. And all of these are problems facing us that we can apply these new technologies in order to come up with solutions. At Georgia Tech, I have quite a number of projects that are focused on developing new algorithms and applications for emerging problems. We focus on problems in biology, such as understanding the tree of life and how organisms have evolved, all the way through understanding RNA viruses. For instance, solving the computational problems to understand how influenza, the flu virus, propagates, or understanding HIV and other RNA virus and related illnesses, as well as looking at problems that require significant amounts of computation. For instance, right now we're doing analyses of massive social networks. For instance, we're looking at the interactions on spaces like Facebook and MySpace to understand how do communities evolve, how do they form, and how to gain information from those networks. On the same token, we're applying advanced social networking algorithms to problems in biology, such as protein interactions, and trying to understand cancer genomics through social networking algorithms. We do a lot of work in our lab on looking at accelerators for computational problems. For instance, we have a very unique center at Georgia Tech, sponsored by Sony, Toshiba, and IBM, on the Cell processor, which is the processor that was built for the PlayStation 3. And we're looking to use that processor not just for gaming and entertainment, but for other applications. So while you may have a PlayStation at home, perhaps you could use that for other purposes that would be very computationally demanding. The Cell processor, we have some exciting projects. One project with a colleague of mine, George Vachsavanos in EC, looks at using the Cell processor for an aircraft early warning system, an early monitoring system. So you may imagine that you're flying on a plane, and in the back of every seat is a PlayStation where you can play your games. But yet that system may have a dual use in understanding vibrations in the aircraft, kind of like when you drive in your car and you feel a vibration that tells you, oh, something may be wrong. So if we could employ this on an aircraft, we may be able to give the pilot a warning that there could potentially be a catastrophic failure and have the pilot land before that event would occur. So we're quite excited to use the Cell processor in applications that expand its use to these very critical problems. For our applications, there is a lot of work that we've done that has expanded our understanding in a number of natural sciences. For instance, we've worked on problems of understanding deep evolutionary histories of organisms from their sequenced genomes. And this is interesting in its own right to understand how life evolved, but this has had tremendous impact in drug discovery and drug design at pharmaceutical companies. And it's been used to understand virus propagation such as influenza or HIV. And so I'm very proud of the work that we've done that has both improved computer science and algorithms, but had a tremendous impact in the real world. At Georgia Tech, we are very collaborative in nature and have a number of projects that are in partnership with industry, with national labs. To highlight one, We are a member of the Center for Adaptive Supercomputing Software for Multi-Threaded Architectures, or CASMT, that's led by Pacific Northwest Labs and includes partners such as Cray, the supercomputing company. In that project, we're analyzing advanced social networking algorithms, trying to understand population dynamics when we have social networks that have millions of folks involved. For instance, Facebook today has about 120 million users, and we want to understand how do social communities form, how do people interact with each other. We also apply those social networking algorithms to other problems. For instance, we are now looking at models of our power grid, trying to understand fault tolerance within our power grid and ways to supply more robust power in the future. As we know, energy is a driving consideration. So I'm excited by partnerships that are so unique in that they require innovations in architecture, working with industry, innovations in algorithms that we do here at Georgia Tech, as well as partnerships on problems of national interest, such as homeland security, protecting our populations, looking at biological problems, as well as security and power supply. We collaborate with a number of industry partners. One that I'll mention is IBM. We not only direct the Sony Toshiba IBM Center of Competence focused on the cell processor, but we've had a lot of engagement with IBM on developing future technologies such as petascale and eventually exascale architectures. For instance, we worked with IBM on the PERCS project, and the PERCS project is the NSF supercomputer that will be deployed about 2 or 3 years from now and will be one of the most capable systems for open science research. We also develop algorithms and systems for the cell processor, and that processor is the greenest processor of any on the market, and it's also used in the most capable system in the world today, the Roadrunner system that sits at Los Alamos, that combines both traditional x86 processors with acceleration by the cell processor. And this is an example of what we're able to do at Georgia Tech that innovates computing technologies and algorithms, but is focused on solving real-world problems, for instance, in sustainability, and also looking at areas of critical importance to national security.